So I think over to Aman, right? So I should not waste time now.
Okay, okay. Thank you. Thanks for hosting me for this series, Biswa. Hi, everyone. So, in today's talk, I'll talk about INC-IDFA, which is an efficient and generic algorithm for incrementalization of any iterative data flow analysis. This work was done as part of my PhD work under the guidance of V. Kishan Nandiwada, who is here to answer all the questions. Okay, moving on. So let's understand what is an IDFA. So I'll just try to keep this talk very basic so that, like people from all the different domains can understand the context well. IDFA stands for Iterative Data Flow Analysis, and it's an important class of compiler analysis where basically we have a control flow graph of the program and try to propagate information on the edges of the control flow graph until we reach some fixed point. This can help us understand various properties of the program at a static time. Some examples are reaching definitions, liveness, points to analysis, constant propagation, and so on. So now during compilation of a program, it may undergo a lot of optimizing transformations. And as a result of these transformations, the data flow solutions or the results of these data flow analysis may become stale and hence they have to be stabilized. So what is the stabilization? It is nothing but making sure that the result of the analysis correctly reflects the modified state of the program or the modified program. There are two types of stabilization or like two options to stabilize. First is if we completely invalidate the data flow information and then recompute it from scratch. And the second approach is if we incrementally update the data flow solution given the set of program changes. The first option is precise and very easy to automate. However, it is clearly inefficient because most of the times the program changes might be very small and only a small part of the old solution might be impacted and might require an update. Second approach, on the other hand, is an ideal case scenario where we would want to have a precise, efficient, and automated scheme. But the issue is we do not know what is the incrementalization algorithm for any arbitrary new data flow problem. So let's understand what is an IDFA with an example. In case of an IDFA or iterative data flow analysis, with each node in the control flow graph, we maintain two flow maps, an inflow map and an outflow map. So inflow map denotes what is the merge of incoming information from all my predecessors. This is denoted mathematically as the mate operator. Outflow map is nothing but saying if I execute this node n, what will be the impact on the incoming information? So that is the outflow map for the node n. And in order to obtain the most precise yet complete solution, also called as the maximum fixed point solution, we employ a standard worklist based algorithm where we will initialize the outflow map of all the nodes with top, which is like some initial value, add all the nodes of the control flow graph to the work list, and then take each node one at a time until the work list is empty. When we extract a node, we will recalculate its in and outflow maps. If the outflow map has changed, that means that node n has new information to propagate to its successors. So we'll have to process the successors again, and hence we will add the successors to the work list. So we do this until the work list is empty, and that's when we say that a fixed point has been reached. Here's a small example. So this program snippet and its corresponding control flow graph, it shows that we are setting variable y to 2, then there is a loop from 0 from 0 to 10, 9, and we have y is equals to ident y. So let's assume that we want to run constant propagation analysis, which is an example of an IDFA, where the goal is to identify what are the possible constant values for various variables at different program points. And this can be very useful to remove unnecessary computations for dead code removal and so on. And the possible values that we model statically are top, integer, and bottom. So top represents the least informative value. That's, for example, the value that we would presume before we analyze any node. Bottom, on the other hand, says the most conservative value, where we say that, okay, I'm done processing the node, but I'm not able to statically identify what is the exact integer value for that. Now, as per the algorithm we had looked at in the last slide, we are first going to add all these nodes into the work list WL. We take one node at a time. After processing node N0, we find that value of Y is mapped to 2, whereas Z is top. And so on, we'll process, let's say, N4, where we know that y is equals to ident y. I do not know what method ident does. So we will say that, okay, I do not know what the value of y may be. So y will be set to bottom, z will remain as 0. We'll process n5, after which the out changes, and hence we will add n2 back again. And finally, the fixed point solution will be that y and z both are bottom in rest of the code. Now, let us say as part of an optimization or some analysis, the compiler identifies that ident is nothing but an identity function. So essentially, L2 is just setting y as y. So it's y is equals to y. It's dead code. Now, the compiler would want to remove that code. So once it removes N4, the issue is we need to stabilize the result, right? So because if we look at N5, it still says that Y is bottom and Z is bottom. But if you look at this loop, there is no writes to Y anywhere in the loop. As a result, this L3 should see value of Y as 2, not bottom. But what we see here is bottom. And so this is the reason why stabilization is required. So in this talk, we'll first discuss about what are the imprecision issues with the standard restarting iterations approach, how we can handle it naively with an approach called as init restart. Then we will discuss about our proposed efficient algorithm inc IDFA, and we'll move on to implementation, evaluation, and conclusion. Okay, so let's start with a standard restarting iterations approach. Let's first understand the meaning of this phrase seed nodes. So seed nodes are nothing but those nodes whose set of predecessors might have changed. For example, N5 in this particular example, if you recall, we had N4 here. After deleting N4, N5 is the node, which is the seed node for this example. Restarting iterations algorithms is something very simple. It says that populate your work list with the seed node, N5 in this case, and then just restart your previous computation. That is, extract a node, recalculate its equations. If there is anything changing at the out, then add the successors and do this until a fixed point is reached, or like until the work list is empty. So we add N5 to the work list, we will process it. We will see that, okay, the incoming information is y is bottom, z is bottom. Once I process z++, I'll have y is bottom and z is bottom. So there is no change in the out. So N2 will not be added back again. The work list will be empty and we will reach the fixed point. So now this is actually a correct fixed point solution, but it is not precise, right? Like correct means like nothing will go wrong here. It is still uh, preserves, or rather it still conforms to all the equations that we have for the data flow analysis. We will see that there is no change in the solution in this example, but the solution is imprecise. It is complete, it is correct but imprecise, sound but imprecise. So now, if you compare,
Sorry to disturb you. So could you spell out what you mean by imprecise here?
yeah, so imprecise means that, let me go back, sorry. Okay, so if I think about it, if I think about the word imprecise in a generic context, what we're trying to say is that we are claiming way more than what we know to be the case. For example, I know that this particular pointer A will point to this exact location M1, whereas statically if I say that no, A may point to M1 or M2 or M3, then that is being imprecise. Like I still have M1 in the solution, so it is correct and safe, but I am
Okay.
being very, yeah, yeah. Does it make sense?
Yeah. Got it. Yeah, thanks.
Thanks. So now to validate that, yeah, this was actually imprecise, let's compare this with comp IDFA, which was clear out the information and recompute. So here, when I recompute the data flow results, we'll see that L3 indeed sees Y as 2, whereas in this restarting iterations approach, Y was set as bottom. As a result, I can actually change this L3 to print 2 instead of print Y, whereas over here, in this other example of restarting iterations, we can't make that change because Y is bottom here. So now let's understand what is the reason behind this imprecision. So the reason is the cycle here. So in this cycle, if you'll notice, when I am processing N5, I rely on the stale value of N3. So one might ask that, okay, what if you process N3 before N5? The issue is N3 will read from N2, N2 will read from N5 and so on, right? So no matter which which node we process first, if we are reading from the stale values, we will continue to get stale values in a cycle. So that's the main thing to remember. cycles are the reason for imprecision. So a very naive two-step algorithm is init restart, where in the first phase we will clear everything which is reachable from the seed nodes, like N5, N2, N3, N6. Their data flow maps will be cleared. And then we will add these things to the work list and restart the iterations. And hence we will get the correct solution. So as you can see, we are able to get the precise solution here, but um, this can be very inefficient, because if, let's say, one of the early nodes is a seed node, then anyway we are going to clear out all the like flow maps of all the nodes, which will be very similar to comp IDFA. So we are not going to gain anything in terms of efficiency. So our proposal is Inc IDFA, which will guarantee precision for all the monotone iterative data flow problems. I'll not go into the word monotone. It will require some theory there. And then it is fully automated because we do not require any stabilization specific information from analysis pass writers. We have four key optimizations and one heuristic. So the first optimization is we will process the control flow graph in terms of SCCs. So like an SCC is a graph where each node is reachable from every other node in the SCC. We will process one SCC at a time. If there is no change in the outgoing information for the SCC, then its successor SCCs will not be processed. So that's the first optimization. Second optimization is that we will not reset the flow maps eagerly. Instead, we will just ignore the imprecise ones. We will look at an example to understand this later. Third optimization is that instead of processing the seed nodes with no correct information or rather no safe information, we will do some other changes so that we are starting with some non least informative value when we perform the initialization step. And finally, in the stabilization step, we will reduce the number of nodes with which we are restarting the iterations, again, with an aim to eventually process lesser number of nodes and reach the fixed point faster. So let's look at the first optimization. So as I said, an SCC is nothing but a subgraph where each node is reachable from every other node, and a graph of maximal SCCs, which is actually a DAG, is called as SCC decomposition graph. So if you remember from the earlier exploration, we know that all the imprecision arrives in cycles of the CFG. Now we know that each cycle of the CFG must be present inside an individual SCC or individual maximal SCC. Hence, we know that if we stabilize one SCC at a time, we will be able to root out all the imprecision. So for example, if we look at this figure, let's assume that S is the seed node. After performing both the steps where I clear the flow maps in whatever manner, and then if I like perform restarting iterations within S1, if the out of A doesn't change, then we know that S2 and the SCCs beyond S2 need not be recomputed. So that's where we make our savings, because after processing an SCC, if there is no change, we can just stop. In the second optimization, we do not eagerly reset all the flow maps of an SCC. Instead, we maintain two maps. First is the set of safe nodes. That is, those nodes whose flow maps will not lead to an imprecise solution logically are called as a safe node. And the way to define them is that if I'm processing SCCs in a topological sort order, then every node in the SCC above my current SCC is already safe. And when I'm processing an SCC, every node which relies on flow maps of the other safe nodes will continue to be a safe node or will become a safe node. Under approximated node, on the other hand, are those nodes for which when processing it, we ignore the potentially unsafe information coming from any of its parents. So we'll again understand this with an example next. And one thing to keep in mind that once we process a node and mark it as safe, we need not process it again in the initialization step. We can just wait till the stabilization step to reach the fixed point solution. Okay, so here's another example. Let's assume we have 1,000 nodes in a cycle here. N1 is print of X. Let's assume that there was something here on this green edge which was deleted, because of which N1 is a seed node. So the work list has the seed node. Safe nodes and under approximated nodes are empty, like the sets are empty. I'll process N1. Now, as I said, we will ignore all the potentially unsafe incoming flow maps. Since N1000 is not a safe node, we will ignore it. As a result, what we will see at the in of N1 will be that X is mapped to top, that the least informative value. Then the out, since I'm not writing to X, will not change and X will continue to map to top. Now this has changed because if you recall earlier it was bottom. In the work list, that's therefore I will add N2 because my out has changed, N1's out has changed, so I will add N2. N1 is now a safe node. Why? Because I did not rely on any potentially unsafe incoming value to calculate the new values for N1. However, N1 is also an under-approximated node. Why? Because I ignored one of its predecessors, which is N1000 in this case. Okay, moving on, I'll then extract N2. Now, if I look at N2, I know that N1 is safe and N0 is also safe because it's from the previous SCC. Therefore, I'll take the incoming information from both of them. My out, however, is excess bottom, which is what the original value was. So I won't be adding N3 into the work list, and hence my initialization step will terminate early. Now, if you compare this with the original case where I'm clearing out all the flow maps instead of just ignoring the potentially unsafe ones, then I would definitely have to process all the 1,000 nodes at least once in the initialization step. In contrast, here we are processing only N1 and N2. Yeah, just to make sure that we are on the same page, if we have any doubts for this slide, I'll pause for any questions.
Can you just maybe say again that how N1 is safe and like what's the under approximation for that? Okay.
Okay, so N1 is safe because it is not relying for the calculation of its incoming information, which is via this green edge. It is not actually relying on any of the potentially unsafe values. So potentially unsafe, so the way to define it, uh, unless and until I have analyzed a particular node, the value that it contains might be potentially unsafe. However, if I'm not relying on any potentially unsafe value to do my calculations, then what I attain is actually a safe value. Does that make sense? The first part?
Yeah, that makes sense.
Okay, okay. And under approximation means that, okay, I said that I'm going to ignore one of my predecessors, like N1000. But that means that I'm actually ignoring one of the potential paths that can actually be taken at runtime. And as a result, what I have right now is not the complete information. So the word under approximation here means that it's not the complete information. It is some incomplete information. If I'm not taking this edge's incoming information, if I'm ignoring it, then I need to eventually make sure that once everything is safe, I should actually read that information and reanalyze N1 to be sure that I'm not losing out on any potential uh, approximation of runtime behaviors. Does that make sense?
Yeah, that makes sense. Thanks.
Yeah, thanks. Okay, so moving on to the next optimization. Okay, so let's define an entry node of an SCC. It's something very logical, like it's any node for which so at least one of the predecessors should be in some prior SCC. That means there is some incoming information into the SCC at this particular node, and in that case we call it as an entry node. So now if a seed node is not an entry node, then it may so happen that it won't have any safe predecessors, just like N1 in the previous example. In that case, the propagation would start with the least informative value, which can be very inefficient because higher up or lower up in the lattice, depending upon how we draw the lattice, farther away we are from the solution, more number of steps we'll have to take to reach the solution. That's the logical way to look at it. To ensure that seed nodes are not processed with top or the least informative value, we actually split the initialization step into two phases. In the first phase, we propagate information from entry nodes up until the seed nodes. Then in the second phase, we start with the seed nodes, like the way we did in the last example. So let's go back to this example to understand the second optimization of initialization step. So here, instead of starting with N5, I'm going to start with N2, which is the entry node for S1. After processing N2 and N3, we know that we're going to get values of Y as 2 and Z as 0. Notice that while processing N2, I am going to ignore N5, right? Because that's the optimization we had seen in the first, uh, that's the rule of the first optimization of initialization step. So as a result, Y is 2 and Z is 0 for N2 and N3. Then after processing this, I'll go to the second phase in which I'll process N5 and I will reach the value Y is 2 and Z is 0. This will lead in general to a quicker termination of the initialization step, or not just initialization step, but the overall stabilization process. Because instead of starting with Y as top and Z as top, I'm starting with Y as 2 and Z as 0, which is much closer to the actual solution. Okay, so then stabilization of stabilization step doesn't require any illustration. It's something very simple where we say that instead of starting with all the nodes that were processed in initialization step, let us start only with those nodes which are under approximated. And we're starting with those nodes, the restarting iterations is applied as before. And then we have proved that it will yield the final MFP solution. Now, let's quickly look at the heuristic that we employ, which is to reduce the frequency of the transfer function applications. So let's first define the notion of access keys. So access keys are those keys. Okay, so let's understand the notion of keys here. So the data flow maps or data flow solution or information can be expressed as a map from some key to some value. For example, I may say variable X has value 2, variable Y has value bottom, and so on. So X and Y are the keys. Among the set of keys, we mark those subset of keys as accessed keys which were read or written while applying the transfer function of n. Now the heuristic is something like this. Let's assume that old inflow map for node n had keys A, B, C, D with these values. And sorry. And the old outflow map, let's assume, had written to values for A and B as VA prime and VB prime. And let's say there were no reads from C and D. As a result, the access keys are A and B. Now, when I'm processing this node n once again, let us assume that the new inflow map has new values for C and D, which is VC prime and VD prime. Since the values for A and B did not change since after the last processing, we know that this transfer function's impact on that set A and B would still be the same. So we'll just copy this value VA prime and VB prime for the new outflow map. Whereas since transfer function is not at all connected to C and D, we will just copy the values, the new values from the new inflow map to the new outflow map. So just by copying the value from old outflow map for access keys and new inflow map for non-access keys, we can actually obtain a result which is same as the result that we will obtain by applying the transfer function. And clearly copying these data flow maps can be much faster than applying the transfer function in most of the cases. We attain a lot of benefits because of access keys heuristic. So now I've made a lot of claims regarding that, okay, if we do this, then that thing can be correct. And then I also made this very grand claim that, hey, this approach is actually applicable to all the possible data flow analysis, even the ones that I have never seen, because someone else might come up with a new data flow analysis going ahead, right? So the question is, how can I be sure that these are actually correct? So for that, we have given a very detailed formalism in the paper. And so by the way, this talk, I forgot to mention, this is published in Uppsala, and I'll share a link with Biswa. Maybe he can like share the link of the paper with the audience so that they can go through the formalism here. In the formalism, we define two key properties on the nodes. First is the safe node, which is nothing but a set of nodes where the flow maps will not lead to imprecise solutions. Second is consistent node, where the equations, the data flow equations that we had seen in the very beginning are satisfied by the flow maps of the node. And the key implication that we prove is that if all the nodes in an SCC are safe and consistent, then the MFP solution has already been reached in that SCC. And then we also like we have formally defined what is a flow graph, a data flow analysis, a data flow solution, and we have provided operational semantics on for INC IDFA on an abstract data flow analysis, where we prove that Ultimately, once the analysis is complete, for all the SCCs, all the nodes are safe and consistent. And we have proved termination, soundness, and precision guarantees of Inc. IDFA with the formalism. So again, the details are in the paper that I'll share. And yeah, I would love to hear your feedback on the formalism. Moving on to implementation and evaluation. So we have implemented all the key components of Inc. IDFA in the IMOP compiler framework. So IMOP is an open source source-to-source compiler framework which was written by us as part of my PhD work. It works for OpenMPC and serial C programs, and it spans over 156,000 lines of code in Java. Uh, we have instantiated 10 specific data flow problems, instantiated Inc. IDFA for 10 specific problems, like stretching definitions, liveness, points to, log set analysis, and so on. And for comparative evaluations, we have also implemented the other stabilization modes, such as comp IDFA, which is nothing but clear the flow maps and recompute it from scratch, or init restart, which is something like clear everything reachable from the seed nodes and then recompute it. So we have performed evaluation on 4 benchmark suites, NPB, Spec, Sequoia, and IM Suite. And we have performed evaluation on two 64-thread platforms, an Intel and AMD platform with 64 GB and 512 GB of memory. So basically the impact of the reason why we performed this evaluation on two different machines is because when we are processing lesser number of nodes, the amount of memory that we are going to generate will also reduce significantly. And the way this will impact the overall compilation time or memory consumption can differ drastically across different JVMs. So yeah, to get a bigger picture clear of how the final end-to-end impact would be of our technique, we performed evaluation on two different architectures here. Uh, the evaluation dimensions were the performance evaluation of Inc. IDFA, which is about IDFA stabilization time and its impact on the total compilation time. Then what is the impact of accessed keys heuristic and also empirical correctness of the final generated solutions. And in order to make sure that we are not running any synthetic experiments, we used a real world client to generate program changes and stabilization triggers. So this is BareLM, which is one of the set of optimization passes in IMOP, which helps to remove redundant barriers from OpenMP programs. So in this graph, we show the speed up of IDFA stabilization, speed up in IDFA stabilization time for Inc. IDFA and init restart as compared to the baseline, which is comp IDFA. So the y-axis here is the speed up, and on the x-axis we have different benchmarks. So we are showing only a subset of the benchmarks here. Uh, so the gains here in the speed up will depend upon the number of nodes that are actually reprocessed during stabilization as compared to the number of nodes that were processed in complete IDFA or comp IDFA. Then the number of transfer function applications that were skipped because of the access keys heuristic. And finally, also on the cost that is incurred to process different types of program nodes, right? Because one application may, for example, reduce processing of 5 nodes, whereas other approach may reduce application of 3 nodes. But what if these 3 nodes had much costlier computations to make? In that case, the savings will be much higher for the case where we reduce these 3 nodes processing versus processing of the other 5 nodes. So okay, and then we noticed that Inc. IDFA is consistently better than Comp IDFA. Like all these blue bars, their values are above 1.0, and I also correlated this with actual number of times the different nodes were processed. For example, we can see that in EP, we receive up to 11x improvement because we ended up processing only 34.4% of nodes as compared to the nodes that were processed in comp IDFA. And as compared to in init restart, we received this 4x improvement from 2.75 to 11 because we again processed only 27.8% of nodes as compared to number of nodes processed in init restart. So if you have any doubts on this graph, will take a minute. Otherwise, I'll move on to the next graph.
So, Aman,
Yes.
so what fraction of overall compilation time is this stabilization time?
Yeah, that's the next graph.
Okay.
Okay.
And the other thing is,
Yeah.
in terms of the absolute stabilization time.
Yeah.
So, like, are they in
Seconds.
seconds, minutes?
Tens of seconds. Tens of
Tenths
seconds.
of
Yeah. And again, I mean, so this is tens of seconds for programs which are sized in like 3,000 to 8,000 or maybe 7,000 lines of code. So if you go ahead with much larger programs, the order of like magnitude for this timelines will also change. Timings will also change. Yeah. Okay, so moving on to the impact of Inc IDFA on the total compilation time. So this is the percentage improvement in total compilation time for the various benchmark programs. Again, for Inc IDFA and init restart as compared to uh, the baseline, which is comp IDFA. These improvements will depend upon the fraction of time that was spent in IDFA stabilization. What is the overall speed up from the previous graph? And then again, some non-determinism that inherently creep in because of the garbage collection overheads when we talk about JVMs. So to give a very high level idea about what this factor C or how this factor C determines these numbers, understand it this way that if an application is using more memory, the GC might trigger, thereby reducing the memory. Whereas if the application is using lesser memory, slightly lesser memory below a certain threshold, the GC might not trigger. So the cost of GC adds up in the compilation time. When we are running the JVM, so that's something which becomes non-deterministic at some in various configurations. Okay, so we can see again that Inc IDFA is consistently better than Comp IDFA, and the maximum gain was obtained for Quake because 46.16 percentage of time, sorry, 46.16 percentage is the improvement. 59.2 percentage fraction of the compilation time was actually spent in IDFA stabilization time. So, Biswa, that's to answer your question about what fraction do stabilization of IDFA take as compared to um, compilation time. So it can be as high as
Yeah,
9.2%.
you have a plot that shows this number for all. I just wanted to see where you got
Have a
11x.
table in the paper actually. No, I mean, because of lack of time, I thought I'll not add all the plots. But yeah, we have lots of data in the paper in tables and graphs. So I think that will give us a more clearer picture regarding that. But
But the
we,
primary contributor is the option A, is it? The fraction of time spent in stabilization, the
for this,
improvement in that part.
yes, it's a mix of A and B, right? I mean, it's more like saying that uh, analogous to the way we say that okay, the maximum benefit we can get in terms of parallelization depends upon the amount of code which is parallelizable, right? So it's just like that, that
I
out of
got it.
100 seconds of compilation time, first we have to identify how much time is spent in stabilization, and then we have to identify what is the best that we can do in that stabilization window. So these are the two main factors here.
Can you just please go to the previous slide?
Yeah,
Benchmark is 11x.
yeah.
Yeah, EP. Okay, so now can you come back to the next slide?
Yeah.
Okay, okay, yeah, thanks.
Okay, thank you.
Yeah, you can continue.
Okay, thanks. Yeah, so I mean, I'm done with the presentation. It went by a bit faster.
Aman,
Yes,
I have a few questions.
yes, yes.
Yeah, this is Anushri.
I agree. Yes.
Yeah, hi. So, this is intra-procedural or inter-procedural?
This is inter-procedural, inter-thread because this is for OpenMP programs. So this is inter-procedural, inter-thread, context insensitive.
Okay.
Yeah.
Okay. So when you identify SCCs,
Yeah.
you look those SCCs can be across procedures?
Yes. So what we work upon is a super graph, which is a combination of control flow graph and something called as intertask graph, which is nothing but edges among the different flush operations, and also the call graph. So it's a combination of all three: control flow graph, call graph, and intertask flow graph.
So this is not ICFG. This is different from ICFG, right?
This is Yeah, I mean, there are multiple names that people have used for it. See, if you, let's say, remove all the parallelism constructs, then this will become like an interprocedural control flow graph. If you
Okay,
also
okay.
add parallelism constructs to that, then we have to model the intertask or interthread
Mhm.
flow of data, right? So
Okay,
otherwise it will be incorrect. So yeah, I don't think there is an alternative because it's more about correctness here rather than precision.
right. I have a couple of
Just
more
maybe
questions here.
one
Uh,
more minor thing should be added, that ICFC is only control. So here it's both control and some form of data is also, because the fence, the the edges from the flushes give us information about not just control but also, I guess, some sort of how the data is going, right?
yeah.
Okay, okay. I'll just have two more questions.
Yes.
So you compared it with comp IDFA and init
Yes.
start, right?
Yes.
Uh, did you try looking into revisor kind of strategy where they also have a heuristic or an optimization where they check only at the return method returns or method calls?
So
Uh,
the issue, Anushri,
so
here
I'm
is.
assuming that in comp, you're
Mhm.
assuming that everything is reset, right?
Correct, correct, correct. Everything
Yeah,
is reset here, which is like the most naive thing that we can do. So that's why that's the baseline because
correct.
nothing can be worse than
Right,
that.
right.
Yeah.
But there are several
No,
optimizations
no.
in
Yes,
the
I mean it's
literature.
like in the literature, I think this paper has more than 130 or I don't recall the exact number.
I have read your paper, so
Okay.
yeah, yeah.
I didn't know that.
I'm just curious that during experiments, do you try that
No, so
check?
the reason is this. The answer is no, and the reason is
Hmm.
this.
Hmm.
What we are proposing is a generic algorithm which doesn't
Okay.
require any specific definition of functions which are defined by the writer of the data flow analysis. So we do not as such have any generic data flow analysis algorithm. It will obviously be interesting to know that, okay, if I am using revisor for, let's say, points to analysis versus IncIDFA for points to analysis, which one will perform better? So the intuition, my intuition says that, or rather even our observations have been that any specific analysis written for the specific subset of data flow analysis or specific data flow analysis will always be better, most of the times be better than a generic analysis. So it's
Right,
more,
right.
yeah, so it's more like that trade-off. So it was like an apple to oranges comparison, and that's why we didn't add it in the paper because we wanted to
Mm-hmm.
define our scope as any generic data flow analysis. If it is not generic, then there is no point in comparing because we know that specific will anyway be better. So we won't
Yeah, so
learn.
you didn't want to restrict yourself to distributive analysis and all those
Correct,
things.
correct, correct. Yes. So there are a lot of restrictions there, right? Distributive
Yeah.
analysis is one, and then some of them will work only on set union and set intersection type of
Mm-hmm.
operators.
Correct, correct, correct.
Some of them will be only bit vectors. So that's why. Yeah. But
Okay.
yeah, that's an interesting question. Yeah, thanks for
Yeah, no,
that.
fair enough. Yeah, thanks. Thanks for answering. Thanks.
I
You
have a
said you.
question. Have you
Aman,
used revisor anytime? Anush, Anushri?
Sorry, I didn't catch your
I
question.
was curious. Have you used revisor?
Yeah, we were actually trying to take that implementation and rerun it, but when we were not able to compile the code, and when we contacted the authors, they say that there is a high mismatch of the current version of suit and the version that was used by revisor, so that
Yeah,
implementation cannot work anymore.
yeah, yeah. Even
So
yeah. I was curious if you could get it to running and work.
no, we couldn't get it running.
Yeah.
But we implemented that logic for functional approach. I have a
Hmm,
paper in ISRI 2022 where we
hmm.
implemented not for IFDS. We have so I'm from TCS Research, and
Right,
we met last week.
right,
Krishna, if you remember with Uday Khaitkar sir,
right, right.
that so we have our own in-house functional approach based bottom-up analysis in TCS research, a proprietary of TCS. So we implemented that logic of comparing data flow values only at the call points and at the return points. That logic we implemented in our in-house tool. So that ways we have our own version of Revisor, which works for C code, not for Java code.
Is it
Okay.
open source, Anushri?
No,
Or
no, no. This is all proprietary. So yeah, yes.
thanks.
All right.
Aman, I had a question.
Yes. Sorry, I'm not
Aditya
able to
here
see
actually.
the screen. You'll have to tell me the name because
Uh,
I'm the screen here. Sorry.
Yeah.
I am Aditya here.
In
Aditya. Oh,
So
oh, now I recognize the voice.
yeah,
Sorry.
I so I had a question actually regarding the evaluation side, right? I mean, see, if you look at the evaluation, right, we are processing less nodes here, so the
Correct.
compilation time would definitely increase. Sorry, decrease. I mean, the improvements would be more compared to a comp IDFA approach.
Correct.
My question was, did you also evaluate, or is there anything on the paper about the a measurement of soundness compared to comp IDFA? Because what I'm thinking is, if you're doing comp IDFA, the analysis has the entire information about your program, right? So
Correct.
the
Correct.
analysis would be, I believe, much more
Is the
precise and sound.
yeah. It's the baseline ground
Have
truth.
you, yeah, have you done that evaluation as well, that
Yes,
comparison?
we did. So what we did was for all the different stabilization types that we had, like comp IDFA being one of them, init restart. We also even ran restarting iterations for comparison later. But if we talk about the precise ones like init restart, inc IDFA, and comp IDFA, what we did was in IMOP, we were able to dump out the program where we were able to annotate each statement and each expression with like each predicate, sorry, predicate and each statement, we were able to annotate the data flow facts in a normalized form that, okay, this is what the data flow information is in a human readable form. We dumped these files via different modes and then we matched the files. So after normalization, all the files matched verbatim. So that means that empirically we were able to show that for all these 24 benchmark programs, plus some other that were not in the paper, I think overall it was 50 something programs that we had evaluated upon. The generated files of the flow maps were exactly the same across different stabilization modes. So yeah, I mean, empirically, we were able to establish that the data flow analysis results that we are getting are as sound and precise as the baseline, which is comp IDFA.
Okay. Is there any formal proof or formalism in the paper, or
Oh,
have you
yes,
done any
yes.
equivalence check compared to the comp
Yeah.
IDFA?
Yes. We have a very thorough formal proof. In fact, I personally believe that's one of the strongest contributions of the paper because it's very easy to come up with various, approaches in which we can incrementalize things. And I'm sure that there is a lot that we can do here. This is just one of the starting points. But what I like the most about this work personally is that we were able to come up with a proper formal, a very thorough formal treatment of the algorithm where we were able to prove not just that the algorithm will terminate, but also that it will give us sound results and it will give us precise results. So the details are there in the paper.
Okay, thank you. And I had another question actually.
Yes, Aditya.
It was so like in case I'm from NVIDIA, so
Mhm.
we typically, so what happens is what we do is we, so there is think of like dependence analysis, right? And
Yeah.
what we do is we try to embed the information of dependencies in the instruction itself.
Okay.
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 So what we were facing a problem couple of days back was we have an analysis which we run, and it kind of computes these dependencies and embeds it in the instruction itself as to how much cycles I have to wait, because
Hmm.
there is a dependent instruction just before
Mhm.
it. Think of
Correct.
like a raw dependency.
Yeah.
So the problem is, the what was happening was we also do some basic block level optimization where we remove some instructions, we add some instructions, we optimize the basic blocks. The
Mhm.
problem was the analysis results were not changing. And one way we could have changed it, we could have ran the analysis algorithm on the updated assembly file. But I
Yeah.
think your approach kind of solves that problem, that you do not have to run an analysis on the entire assembly file, right? So my question was, how easy would it be, or what it takes to, if I want to use your approach for a problem like dependence analysis, if I want to recompute these dependencies and try to um, add that in the instruction. So
So I'm curious.
what
I mean,
is the,
yeah, in order to address that, I need to understand first, like, what is the approach we are using for calculating the dependency results? Like, is it like a reachability kind of algorithm,
yes,
or is
yes,
it a data flow
yes.
analysis based algorithm?
It's a reachability based algorithm.
Okay, fine. Should be doable. But again, I don't think. See, there are a lot. I'm sure you will appreciate this fact that there are a lot of complexities that may come into picture when we actually go down to the code level and look at the things. In terms of idea, in terms of any known limitations, I don't think that there should be any constraints in applying our algorithm to the context. But unless we actually look at the code base, I don't think I can give a definitive answer on that. Krishna, would you want to add to this?
No, I think I mean, the idea is generic enough that one can kind of hope with reasonable this thing that yes, one will have good success with this. But if we have more details, probably we will be able to do better.
Okay, and thank you. And Aditya, one more point. So you said that the results are not getting stabilized, right? So just to clarify, along this line, we have two works. One is INC-IDFA, which is nothing but an incrementalization algorithm. It, for example, doesn't define that, okay, this is the compilation point where I should run myself, or these are the set of changes that I should take into account. These things are in fact done by our prior work, which is homeostasis. So that one was published in Toplas, and that work basically ensures that for any compiler, it's a compiler design actually. So it says that whenever homeostasis has been implemented as part of a design of a compiler, then whenever there are any stale results, these results will automatically be stabilized uh, before they are being read after a transformation has taken place. Like, for example, removal of some instruction from a basic block in your case. After that, if I'm trying to read from the dependence information, homeostasis will automatically ensure that the results have been stabilized. This work, the one that we discussed today, is more about how that stabilization can be made better, because the default approach would have been comp IDFA, which is inefficient. So we are saying that, okay, this is the incrementalization algorithm, but the underlying framework which triggers the algorithm is the top class work, which is homeostasis. So yeah, I think even that one would be very much connected to the problem that we are discussing.
Yes, I think, yeah, that's where I got confused. Actually, I was looking at your homeostasis work,
Okay, yeah,
and yeah, now I think that clears the confusion.
okay, okay,
Thanks.
thanks. Yeah. Okay, so I'll go on to the conclusion. Um, so we have looked at INC-IDFA, which is a new, precise, generic, and efficient algorithm. It is generic because it's fully automated. We do not require any information specific to a data flow analysis in order to incrementalize it. In fact, in IMOP, what we have is an implementation of INC-IDFA, using which we were able to automatically incrementalize 10 different instances of IDFAs without touching their code in any sense. We just had to extend the particular class. No, actually, we did not have to do even that. That was also part of the whole hierarchy of IDFAs already. Okay, so then as discussed, we have given formalism for proofs of soundness, precision, and termination guarantees. As discussed, this paper has been accepted, and I'll be presenting this paper as part of OOPSLA 2025 in Singapore. I think next week, sometime like 17th of October is the date. So in case if you're attending OOPSLA in person or virtually, I would be like glad to catch up and meet you in person. And thank you for attending this SIS talk, and thank you, Biswa, for like organizing these series. I'm sure these are very helpful, and we should have more and more of them. So yeah, something
Thanks,
happened.
Aman.
There's some okay. I'll stop the screen sharing.
You have a hard stop at 4, right? So
Yes, 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 yes.
Yeah, maybe I think we should wrap it up.
Yeah. Yeah. I have stopped the sharing so we can have generic discussions, if any, and then we can.
Let me stop the recording then.
Okay. Yeah, thanks.